Let's talk about binomial distribution. Consider a fixed number of observations n. Examples are like 15 tosses of a coin or 10 light bulbs taken from a warehouse. Then each observation is classified into one of two mutually exclusive and collectively exhaustive categories. The categories can be head or tail for tossing a coin, or effective and not effective for a light bulb. And then we denote the probability of being classified as event of interest, P, is constant from observation to observation. So if we are interested in the probability of getting a tail, then saying this is the probability of getting a tail, P, and P is the same each time when we toss the coin. And because the two categories are mutually exclusive and collectively exhaustive, when the probability of the event of interest is P, then the probability of the event of interest not occurring is 1 minus P. The value of any observation is independent of the value of any other observation. Here are a few applications of binomial distribution in business. A manufacturing plant labels items as either defective or acceptable. Or a firm bidding for contracts will either get a contract or not. Or a marketing research firm receives survey responses of yes, I will buy, or no, I will not. Or new job applicants either accept an offer or reject it. Suppose that we toss a coin and the coin is fair. The event of interest is obtaining the heads, and you are going to toss the coin 3 times. In how many ways can you get 2 heads? So the possible ways include head, head, tail, head, tail, head, and tail, head, head. So there are 3 ways you can get 2 heads. The situation is actually very simple. So we just put down, write down on the paper possible ways like we did. But what if the situation becomes more complex? Then how can we list or how can we count the number of possible ways? This is actually a combination. The number of ways selecting x out of n objects is n factorial divided by x factorial times n minus x factorial. So applying this formula into the example, we can see the number of ways is actually 3 factorial divided by 2 factorial times 1 factorial, which is equal to 3. This slide shows the formula for the probability of the variable x, taking the value lowercase x given the sample size n and the probability of event of interest p. So this is the probability of observing x events of interest given n and p. The event of interest occurs x time with the probability p. So here we have p to the x, and the probability of not having an event of interest 1 minus p, and this occurs n minus x times, so that's why we have 1 minus p to the n minus x. And considering the number of ways to get x from n, here we have n factorial divided by x factorial times n minus x factorial, and that's how the formula is formed. An example is, let's flip a coin 4 times and let x equal to number of heads. Then n, which is in sample size, is equal to 4. The probability p is 0.5. Here you assume we have a fair coin. So 1 minus p is also 0.5. And x can be 0, 1, 2, 3, and 4. So plug those in the formula, we can find the probability of the variable x, taking each value from 0 to 4, given n and p. First calculation example for binomial distribution. Suppose the probability of an invoice payment being late is 0.1. What is the probability of one late invoice payment in a group of 4 invoices? Here we write out all the inputs. So x is equal to 1. N, which is the sample size, is equal to 4. And the probability p is 0.1. So just plug those in the formula to calculate probability of x equal to 1, given n equal to 4 and p equal to 0.01. We get 0.29 something. Another example. Suppose the probability of purchasing a defective computer is 0.02. What is the probability of purchasing 2 defective computers in a group of 10? So here x is equal to 2, n is equal to 10, and the probability p is 0.02. Plug those in the formula to calculate p of x equal to 2, given n equal to 10 and probability p equal to 0.02. We get this result. The shape of the binomial distribution depends very much on the value of the probability p and the sample size n. If n is equal to 5 and p is 0.1, then the shape of the distribution looks like the graph in the upper part. And if we increase the probability to 0.5, then it looks like this. Here are some characteristics of the binomial distribution. The mean mu is actually equal to the sample size n times the probability p. The variance sigma squared is n times p times 1 minus p. And from there we can easily get the standard deviation sigma, which is the square root of n times p times 1 minus p. Let's go back to the example in the previous slide. We have the sample size n equal to 5 and p equal to 0.1. So plug those numbers in the formula for mu. Mu is equal to the sample size n times the probability p. We get 0.5. And the standard deviation is equal to square root of n times p times 1 minus p. We get 0.67 something. When we increase the probability p to 0.5, what we get for mu is 2.5, and for sigma is about 1.12. In R, we can use 4 functions for the binomial distribution. dBi norm, this is D is for density, Bi is for binomial. Bi norm is for binomial. This is to calculate the probability of x The second function, PBI norm, this calculates f of a q value. Basically, it is p of x less than or equal to q, and lower tail parameter is by default true. If lower tail is false, then we would calculate p of x greater than or equal to q. The log p parameter is to return the log probability, but usually we set it to false, and that is the default value. QBI norm. QBI norm is to calculate the smallest value x for which f of x greater than p, and this is usually for calculate quantiles. And the last function is RBI norm, which is to generate n random numbers from the distribution. Now let's say you have an example. A corporation X is buying 150 computers from Dell, and it's known that the motherboard used in the computers have the probability of 0.12 having a certain defect. Now let's see how we can solve the questions in the notebook.